Hello there. This video is intended for Columbus Public Schools secondary science teachers, particularly physical science teachers. If that's not you, that's fine. You can feel free to check out what I have to say about the universe and whatever the heck this is. But that's the intended audience. And my name is Chris Orban. I'm a member of the Ohio State University Center for Cosmology and Astro-Particle Physics. And we are giving away to secondary science teachers, particularly physical science teachers, this thing which I'm going to talk about in just a second. So we're very happy to do this. There's no strings attached to it. We don't need to know how many students are seeing this thing. I can tell you that this base that we're giving you does not have a camera in it or anything to surveillance your students or something like that. So this is for you. We trust you as educators to use this, and our goal is to help you to teach the universe standards that's in the Ohio Science Standards. And an interesting thing about me is that, and just as a disclaimer, I don't speak on behalf of the Ohio Department of Education, but I was very fortunate to be a member of the committee that kind of helped to update the universe portion of the science standards. So I'm going to give you my perspectives on that in just a minute. Now, what is this thing? What in the world is it? That's a good question. So this is a laser etched piece of glass, and before I show you where we got it from, I just have to say that please do not leave it in the window, because this thing can focus light. So if the sun shines on it, it could potentially focus that. It could start a fire. It could damage people's eyesight. So please don't leave it in the window. Don't shine a laser pointer at it. We're providing this to you as is. We don't have replacement parts. We don't have any of that. So please be safe with it. So we didn't create this at OSU. It came from a company in Germany, and so they were the ones that figured out how to do this. And the idea is that there's hundreds of thousands of laser etched dots in this thing, and each one of these dots represents essentially one galaxy. So this is not the Milky Way and our neighboring galaxy Andromeda and the Triangulum galaxy. This is hundreds of thousands of galaxies. This is what we think the universe looks like on some of the largest scales that we could even imagine. And there's a couple of things that I'd like you to understand. So this is often called the cosmic web. So there's kind of a spider web type appearance. And the reason that happens is that as time goes on in the universe, the regions that are denser, they tend to become more dense. So for example, this part kind of started a little bit more dense, and as time goes on, it gets more and more and more and more and more dense. Right? Same thing over here. So this part started off a little bit denser than other areas, and gravity is attractive, and so this denser area attracted more material into it. And what happened is that these areas got denser and denser and more clumpy, and then they pulled material from other areas into it. And so while we're creating these structures, sometimes this is called filaments, sometimes this is called walls, that sort of thing. While we're creating these structures, we're also creating these voids, these areas where matter has kind of been emptied into the denser regions, again because gravity is attractive and it's pulling the matter into the areas that have more mass. More mass means more gravitational force, and so this is what happens as time goes on in the universe, and the effect of it is what we typically call the cosmic web. And there's people at Ohio State that spend all day, every day, studying the cosmic web to see what we can learn from it. So we love the idea of this glass sphere, of kind of showing it in 3D in all of its majesty for your students to see. Now, the thing that I want to emphasize, though, is that this sphere is not meant to represent the entire universe. So what I want you to do is I want you to imagine that these wispy things fill the entire room that you're in. So anywhere that you look, you see these you kind of see these wisps. Your entire room is just filled with all these galaxies. And we live on one of those galaxies. I don't know, maybe this one. Maybe that one, I don't know. Maybe we live on this one. And then we can only see a certain part of this kind of wider universe, this wider cosmos. And so imagine that we're here, and there's only been a certain amount of time since the universe began for light to reach our telescopes. So there's this wider universe that we think exists, but the part of the universe that we can see is called the observable universe. And so this sphere is kind of like the observable universe, but that doesn't mean that it's the entire universe. We think that the universe extends further than what we can see. So let's do a thought experiment here. So let's imagine that you're a galaxy that's out like on the edge of this thing. So you're all the way, so you're inside the sphere of our observable universe, and we're observing this galaxy with our telescopes. And the question is, what do we think this galaxy sees, right? Because if you just think about it from this toy here, right, you might imagine that that galaxy might see a night sky that is sort of half filled with galaxies, and the other half of the night sky, there's no galaxies at all, right? If that really was the edge of the universe. Well, do we think that that's really what that galaxy is seeing? No. We think that galaxy sees a night sky that's overall very similar to the one that we see, sees galaxies all over the place. And the idea is that the galaxy that's out on the edge, it can see the galaxies that we can see to a large degree, but it can also see galaxies that we can't see because there hasn't been enough time since the universe began for the light from those galaxies to reach us, but there has been enough time, because it's closer to those galaxies, for the light from those galaxies to reach this galaxy that's on the edge. So we think the universe exists beyond what we can see, and that the part of it that we can see is similar to the parts that we can't see, is the basic idea. So again, this is kind of a representation of the observable universe, but we think that it goes beyond that. Now that we've established that, which is a little bit mind-blowing already, get ready for the next truth bomb, okay? Because the next truth bomb is that there's no center to the universe, okay? So the best way to explain that is that if this is us here, if that's the Milky Way, the observable universe that we can see, we can point our telescopes in any direction and receive light from any direction. So of course the observable universe that we can see is going to be in the shape of a sphere, right? But that doesn't mean that the universe itself is in the shape of a sphere. That doesn't mean the center of the universe is at the center of this thing where we are. That just means that the part of the universe that we can see, because there's a certain amount of time that has happened that light can reach us, happens to be in the shape of a sphere. Another thing that we notice, there doesn't seem to be any obvious evidence that the galaxies that we see over that way and the galaxies that we see over that way have any big differences towards them, that would suggest that the center of the universe is sort of like, over here, or that everything's rotating around this point, that sort of thing. So the universe does not have a center in the same way, for example, that the Milky Way has a center. So if you ask any amateur astronomer, what direction is the center of the Milky Way galaxy, they say, oh, well, the center of the Milky Way galaxy is over in the constellation Sagittarius. So you can turn your telescopes that way. But then you ask, all right, well, what direction is the center of the universe? They can't tell you, because there is no center of the universe. There's no obvious direction in which things are pivoting or moving or anything like that. There doesn't seem to be any special direction in the sky that would suggest that. And so with this sphere, one of the ways you can kind of try to teach that is that there's nothing special happening at the center of this thing, right? The little particles at the center aren't really any different than the particles in any other place. There's no real preference for this, there's no real difference between the dots that are sort of over here and over here. And so that's true inside of the observable universe. It's also true even bigger than that. There is no center to the universe. As you probably know, there's a big thing I haven't talked about yet, which is that the universe is expanding, right? So we've talked about how over time gravity acts on the denser regions of the universe and making it more and more clumpy, and making the less dense regions less and less dense, and making this cosmic web. But there's also an important thing that's happening, which is that the universe is expanding. And so that same process is happening as the universe expands. So this is what it looks like. So I'm going to play this video. So things are expanding, right? Things are getting clumpier. The voids are getting more void-like, right, as materials falls onto these denser regions. But all of this is happening at the same time. And so everything is expanding away from everything else in every direction you can think of. But it's still true that galaxies are forming, these filaments are forming, the voids are forming, that sort of a thing. Now, if everything is getting further away from each other, there's an interesting thing that implies, which is that in the past, things must have been closer and closer together, right? So maybe the universe was smoother, but overall the density of the universe was higher. Overall the temperature of the universe was higher because things were closer together. And if you think about what the universe's beginning must have looked like, that would have been a very hot, very dense state, which, of course, as you probably know, because you watch CBS television, it's called the Big Bang, right? But the thing is that the Big Bang was not from a single point, because there is no center to the universe. Instead, the Big Bang happened everywhere. And so if we go to the Ohio Science Standards, it kind of talks about that, right? So this is the page that talks about the universe. So it was last updated in 2018 there. And it talks about the Big Bang. So the Big Bang model is a broadly accepted theory for the origin and evolution of our universe. I think most of the time Big Bang would be capitalized, but okay. It talks about 12 to 14 billion years ago, the portion of the universe seen today. So again, this is not the entire universe, right? This is the observable universe, was only a few millimeters across. So again, that doesn't mean that at the beginning of the universe started with a point. That means that the observable universe, the part of the universe we can see, was much, much smaller in the past. Well, insanely smaller in the past than it is right now, right? According to the Big Bang theory, the contents of the known universe expanded explosively into existence from a hot, dense state 13.7 billion years ago. And after the Big Bang, things moved apart, things cooled down until the point where atoms could form, neutral atoms. And then gravity pulled those atoms together until stars could form, and those stars would clump together to make galaxies and that sort of a thing. And then it also talks about something I haven't yet mentioned yet, is the Hubble law and redshift and that sort of stuff. So, but in any case, there's the Big Bang, there's your hot dense state, there's how things used to be much closer together. Now, the Hubble law, some people refer to as the Hubble Lemaitre law. We did a nice video about that on the STEM Cutting YouTube channel, which I encourage you to check out. And there's even a hands-on activity that you can find there, where you take a rubber band and put paper clips, and you cut out these little galaxies, and you show that as you stretch the rubber band, the distance between the galaxies all spread apart, and the further away those galaxies are from each other, the faster they're moving apart, if you're just sort of stretching the entire rubber band like you normally would. So I encourage you to check that out as kind of a next thing. If you would like to post a picture of you and your universe sphere to social media, and you want to tag the OSU Center for Cosmology and Astro-Particle Physics, you can find them on Facebook. They're also on Twitter, or you can just write, OSU Center for Cosmology and Astro-Particle Physics. That would be great. Another thing that you can do that I'd encourage you to check out is that there's a planetarium show that's related to this YouTube video I just talked about. It's a planetarium show called George Lemaitre and the Discovery of the Expanding Universe that's playing only at OSU Planetarium. And you can fill out a form to request a classroom, like come to OSU and see the planetarium type presentation of that. And so I hope that you consider checking that out. And I hope that you consider checking out some of the public talks that the OSU Center for Cosmology and Astro-Particle Physics does, like the Beard lecture, so there's a link to that in the description. So thanks so much for your attention. I hope you enjoyed these things. We've enjoyed looking at them as long as we have, and we're very excited to put them in the hands of educators where we can share the joy of astronomy with your students. So thanks for your attention.